The planned supports for the roof of a building form scalene triangles of different sizes. Explain what is meant by a scalene triangle. Well, a scalene triangle has three unequal sides. So if we were to draw a rough sketch of a scalene triangle, if we use a tick to indicate the length of this side, then we would have to use, say, a double tick for this side here. It doesn't mean that this side is twice the length of this side. It just means that these two sides have different lengths. Now the third side has a different length from the other two sides, so we could put three ticks on this side here. So that indicates that the three sides are different. The triangle EFG, this one here, is the image of the triangle CDE, this one here, under an enlargement, and the triangle CDE is the image of the triangle ABC under the same enlargement. The proposed dimensions for the structure are length of AB equals 7.2 meters, length of BC equals 8 meters, and length of CD equals 9 meters. Angle DCB is 60 degrees, so DCB is the angle between the arm DC and the arm CB, this angle here. We want to find the length of FG, that's this length here. So this triangle is the image of this triangle under an enlargement. When we do an enlargement transformation, corresponding sides are parallel. So DE is parallel to FG. DE corresponds to side FG in these two triangles, and CD is parallel to FE. Of course, CE is parallel to EG. We also have that CDE is the image of ABC, so BC is parallel to DE and BA is parallel to DC. So we've got some corresponding angles here. Let's call this angle X. X equals this angle here, because this line is parallel to this line, and we have this transversal cutting across. So the angles indicated with the letter X are corresponding angles. Here's another pair of corresponding angles. These two angles, which I'm calling Y, because this line is parallel to this line. So X plus 60 plus Y is 180. X plus this plus Y equals 180, so this is obviously 60. That's pretty clear from the diagram that it's 60, but anyway, just proved it more exactly here. Let's look at the enlargement factor. Let's get a pair of corresponding sides. So in triangle CDE, the side CD corresponds to the side AB in the triangle ABC. They're both opposite angle X. So we want to see what the scale factor is to scale a length of 7.2 up to a length of 9. So we take 9, that's the length of DC, and divide it by BA, which is 7.2, we get a scale factor of 1.25. So now we can find out what DE is. So DE is got by scaling BC up by the factor 1.25. So we see that DE is 1.25 multiplied by BC. So we have 1.25 multiplied by this length here, which is 8. 8 ones are 8, 8 quarters are 2. So this gives us 10. It's in meters. So this here is 10. And of course, then to get FG, we just need to scale this side up by a factor of 1.25. So FG is 12.5 meters. Part 3. Find the length of BD correct to 3 decimal places. In the triangle BDC, we have two sides and the angle in between. To find the third side, we use the cosine rule. The sine rule won't work here. So this side is 8, this side is 9, and the angle in between the two sides is 60 degrees. We call the side that we're looking for side little a. When we're looking for a side, label it small a. The cosine rule says that a squared equals b squared plus c squared minus 2bc cos of capital A. Notice that small a is opposite capital A. The capital letter stands for an angle. So we label the side we're looking for small a. So if small a is this side, then capital A is 60 degrees. Small b and c are the other two sides. It doesn't matter which we call b or which we call c. Let's call this one small b. Let's call this one small c. So we plug the values into this. So a squared is equal to 8 squared plus 9 squared minus 2 times 8 times 9 times the cos of 60 degrees. So we plug all this into the calculator. 8 squared is 64. 9 squared is 81. Minus 2 times 8 times 9 times the cos of 60 degrees. So we get 73. So a is the square root of 73. Put 73 to the power of a half. The 3 decimal places, this answer is 8.544. And this is in meters, because the other sides were in meters. The sine rule won't work in this situation, because you would have to say a over sine a equals b over sine b. If we use this angle, this side for b, then capital B would be this angle, and we don't have it, and we have no way of getting it, because we've only got one angle in this triangle. Or if we use this side as small b, then capital B would be this angle. So you can see straight away that we can't use the sine rule. So when you can't use the sine rule, use the centre of the enlargement is O. Find the distance from O to the point B. Okay, how do we get the centre of the enlargement? Well, we know that CDE, triangle CDE, is the image of triangle ABC under the enlargement. So D is the image of point B under the enlargement. So to find the centre of the enlargement, we would need to extend this line, the line through B and D, back along. We also know that C is the image of point A under the enlargement. C in this triangle is the image of A in this triangle. So the line joining A and C connects back to the centre of the enlargement, which is at O. So I'll draw that sketch here. So I've drawn in the line AB and the line CD. We know that AB is parallel to the line CD. That was I explained that earlier. So where the line joining AC meets the line joining points B and D, we have the centre of the enlargement, which is called O. Now we have a few distances here. We know that AB is 7.2 meters long, and we know that DC is 9 meters long. We also know that BD is 8.544 meters long. We want to find the distance of O to B. Well, this we can use a theorem that we talked about before, which is a theorem about a triangle and a line drawn in the triangle which is parallel to one of the sides. So we're looking at the triangle ODC, and this line AB is parallel to DC. So that theorem tells us that if we take this distance here, OD, and divide it by OB, do that in a different color, then we get the same answer. If we take DC, which is 9, and divide it by AB, which is 7.2. So to make the notation easier, I will call OBX to make the notation easier to write down. OB is x, and then OD is x plus 8.544. So now we know that if we take 9 and divide by 7.2, we'll get the same answer if we were to take OD, which is x plus 8.544, and divide it by OB, which is x. So you can see that the distance from O to D is the distance from O to B, which is x, plus the distance B to D, which is 8.544. So we have this ratio here, and we just cross multiply. We just have a single fraction on each side, so we get 9x equals 7.2 times x plus 7.2 by 8.544. Actually, we could have done this a bit more easily, and I will just do this a bit more easily now by realizing that 9 divided by 7.2 is 1.25. That was the scale factor of the enlargement. So we can replace this with 1.25. Just makes it a bit easier. So we just multiply both sides by x. 1.25 times x equals this thing here by 1, x plus 8.544. Bring all x's to one side. 1.25x minus 1x is 0.25x equals 8.544. So to get x, then we take 8.544 and divide by 0.25. So we get 34.176. Now, yeah, that's our answer. That's in meters. A condition of the planning is that the height of the point G above the horizontal line BF cannot exceed 11.6 meters. Does the plan meet this condition? Justify your answer by calculation. So we want the height of G above the line BF. BF is this horizontal line here. So by height, of course, we want the perpendicular distance of the point G to this horizontal line. So we need to calculate this distance to see if it exceeds 11.6 meters or not. Remember, the scale factor is 1.25, so the sides of these triangles are scaled up by a factor of 1.25. 1.25 by 8 is 10, 1.25 by 10 is 12.5. So the perpendicular height of this triangle here is also scaled up by a factor of 1.25 each time. So if we can find this perpendicular height, then multiply by 1.25 to get the perpendicular height of this triangle here, and then multiply by another 1.25 to get this perpendicular height of this triangle out here, which isn't completed. So we just need to get this perpendicular height. So what do we know about this triangle? This is 8, this is 9. The other side is 8.544. We also have an angle. This angle is 60 degrees. So we're interested in the perpendicular height of this triangle here. So even though the question only talks about enlargements of triangle ABC and triangle CDE, it turns out that the same enlargement applies to triangles BCD, DEF, and FG, whatever, we can call this H over here. See, we're enlarging these three triangles also. We're enlarging the sides by a factor of 1.25. Well, not just the sides, the three sides, but also the perpendicular height by a factor of 1.25. Now, to find this length here, it would be a mistake, of course, to say that this angle is 30 degrees and this angle is 30 degrees. We can't do that because this triangle is not isosceles. This is 8, this is 9. These are two different sides. If these two sides were the same, then the perpendicular height would indeed bisect this angle of 60 degrees into two equal angles of 30 degrees each. But that doesn't happen, so we can't do that. So I get rid of that. These angles are different, and we don't know what they are yet. Actually, we won't work with angles at all. We will consider the area of this triangle. This is the easiest way to do it. The area of this triangle is half one of the sides, and we take this side as base, multiplied by the perpendicular height. So I'll call this distance that we're looking for h. So that would give us the area. We could simplify that a bit. 0.5 multiplied by 8.544. That's 4.272. 4.272 times h. Now we can get the area of this triangle another way, by getting half the product of two of the sides by the sine of the angle in between the two sides. So I'm taking the sides 8 and 9, and the angle in between them is 60 degrees. So this formula is written down in your tables as a half AB sine capital C, where small a and small b are these two sides, and capital C is the angle between them. Capital C is opposite small c. Small c is 8.544. So this is the formula that I'm using. Anyway, I'll just erase all of that. Gets in the way. Basically, in words, you just want half the product of two sides times the sine of the angle in between the two sides. So once you have two sides and an angle in between, you can get the area of the triangle. So let's do that. So we've half of 8 is 4, multiplied by 9, multiplied by the sine of 60. So that's, let's say we round this to one decimal place. We get 31.2. 31.2 meters squared, because the sides are in meters. But of course we got the area the other way, by half the base times the perpendicular height. If we take this as base, then this h that we're looking for is the perpendicular height. It's 4.272h. So 4.272h equals 31.2. So that means that h is 31.2 divided by the coefficient of h, which is 4.272. So to one decimal place, that's 7.3 meters. So now that we know that the perpendicular height of this triangle is 7.3 meters, we just multiply by 1.25 to get the perpendicular height of this triangle here. Oops. 7.3 multiplied by 1.25 is 9.125. So this here is 9.125. And finally, to get this here, we just multiply this by 1.25. Just multiply by the scale factor. Everything, all the lengths are scaled up by 1.25. So we get 11.41. Let's write that down to 2 decimal places. So the condition is that the distance of G to the line BF does not exceed 11.6, and indeed it doesn't. We get 11.41, which is less than 11.6. So the answer to part 5 is that the plan does indeed meet the condition.